In this next unit, we're going to learn about chemical reactions and how we represent chemical reactions. Chemical reactions, also known as chemical changes. Usually I use the term chemical reaction. Here's some evidence for a chemical reaction. So how do we know if when we mix chemicals together that a chemical change occurs? Well, there's some evidence. One, and we'll see each of these or all of these in the labs that will be performed in this class. One is a color change. So you take two, say, colorless substances, mix them together, and what that turns into has a different color. That's a sign of a chemical change. Another one is the formation of a gas. So again, you mix two chemicals together, and a gas is produced during that reaction. Now, if the reaction occurs in solution or occurs in a liquid, what would you actually see if a gas is being produced? Go ahead and think about that. Anytime a gas is formed in solution, what you'll see is bubbles. So bubbles indicates the formation of a gas. Another sign that a chemical reaction has occurred is the formation of a precipitate. The definition of a precipitate is a solid that forms in solution. So again, you take two solutions, mix them together, and one of the things that you make is a precipitate or some solid, a substance that is insoluble in water. So I'll have you memorize those solubility rules so you can predict which substance that is produced in a chemical reaction is the precipitate. And then lastly, energy is absorbed or released. So typically this is in the form of heat or light. And so this tells us if the reaction is endothermic or exothermic. So we can observe this by a change in temperature that occurs. So if the temperature changes when we mix chemicals, that's a sign that a chemical reaction has occurred. If the solution that the reaction occurs in, let's say it occurs in solution, if the solution's temperature increases, that is a sign that the reaction is exothermic. And if the temperature of the solution decreases, that is a sign that the reaction is endothermic. Now let's take a look at an example of what we call a chemical equation. So a chemical equation represents a chemical reaction. So let's take a look at this example here. So unfortunately, we get to miss out on a great demonstration. Typically in the past, I've shown this reaction to the students. So I'll take a balloon filled with hydrogen gas. Hydrogen, like helium, is less dense than air. So it looks like a regular helium balloon, but it's not helium inside, it's hydrogen. And then I hold a flame to that balloon, a candle flame, and I allow the hydrogen in the balloon to react with the oxygen in the air. And this reaction is extremely exothermic, explosive reaction. So hydrogen gas reacts explosively with oxygen. All right, so let's take a look at the aspects of this chemical equation. First of all, the substances that we start off with, which are called reactants, are shown on the left side. So we always read equations from left to right until later on in the year we'll read some equations in both directions actually. But for now, left to right. So what you start off with goes on the left-hand side. We call those substances the reactants. They are separated by an arrow. Please do not put an equal sign there. A lot of times students want to put equals. This is not a mathematical equation. This is a chemical equation. So put an arrow, and that's the reactants are separated from this arrow from the products, or what you end up with. So on the right side are the substances, or substance in this case, that is produced during the chemical reaction, or that is made. And again, we call those the products. Notice that each substance taking part in the reaction is represented by its correct formula. So remember, hydrogen is diatomic. And so we don't want to ever write just H in a chemical equation, so we write it as H2. Likewise, oxygen is diatomic, so O2 for oxygen. And then the water that is produced is H2O. So always represent each substance that participates or that's involved in the reaction with its correct chemical formula. Something else to notice too, it's not in the notes, but underneath the formula of each substance, I've written a G. So we also want to indicate the state of matter of each substance involved in the reaction. So hydrogen is a gas, oxygen is a gas, and the water that's produced because of the exothermic nature of this reaction is water vapor. So it is a gas as well. So for any liquids, we would put L. Solids, we put S. I believe your book for solids puts Cr for crystalline solids, but we're going to put an S for any solids. And then for any aqueous solution, a substance that is dissolved in water, we'll put AQ for its state of matter. So we'll see examples of each of these in just a bit. Next up, the coefficients. Those are the numbers written in front of the formulas. The coefficients represents the relative numbers of particles that take part in the reaction. So notice there's not a number written in front of the O2. That is implied as a 1, so we don't have to write the number 1 for a coefficient. And so I would read the coefficients here in order. So if I ever ask you for the coefficients, give them to me in order. So for this reaction, the coefficients are 2, 1, 2. So we have 2 molecules of hydrogen that react with 1 molecule of oxygen. In that arrow, we say to produce 2 molecules of water. So that's how we read that equation. Now those coefficients are really important, as we'll see in a minute. It's because of this. There must be the same number of atoms of each element on both sides of an equation. Remember, when a chemical or physical change for that matter occurs, mass is conserved. Law of conservation of mass states that the combined masses of what you start off with is equal to the combined masses of what you end up with. So to show that mass is conserved during a chemical reaction, we use these coefficients to do something called balancing the equation. We want to make sure there's the same number of each atom on both sides of the equation. So take a look. How many hydrogens total are on the left? There are 4 of them. So we multiply the coefficient by the subscript. How many hydrogens on the right side? Each water has 2 hydrogens. There's 2 waters, so that's 4 hydrogens. So we got the same number on both sides. Oxygens on the left, we have 2. Oxygens on the right, each water has 1 oxygen, but there's 2 waters, so that gives us 2 oxygens. So both hydrogen and oxygen are balanced. Go ahead and turn to page 225. Pause the video if you need to grab your textbook. Starting in the middle of the page, we see propane reacts with oxygen. It says here to yield or to produce carbon dioxide and water. So go to the bottom of the page, and it walks you through those pictures how many of each atom there is in the reactants and in the products. So we have 3 carbon atoms on the left, 8 hydrogen atoms, and 2 oxygen atoms all on the left side. Right side, so far, 1 carbon atom, 2 oxygens in the carbon dioxide, 1 more oxygen in the water, and 2 hydrogens. Go ahead and turn the page. All right, so let's go ahead and balance the carbon first. So we have 3 carbons on the right. We have 3 carbons on the left. We want 3 carbons on the right. And so we're going to put a coefficient 3 in front of CO2. You can see that at the top of the page. So that fixes carbon. Let's go down to the next set of pictures. Next thing we want to do is balance the hydrogens. So we have 8 hydrogens on the left, and then we're going to add a coefficient 4 in front of H2O to make 8 hydrogens on the right. And then lastly, we'll want to balance oxygen. Well, if we have 3 CO2s and 4 H2Os, I'm looking still at the middle of the page, that gives us 10 oxygens. So we need 10 oxygens also on the left side. So if you look at the very bottom of the page, we're going to put a 5 in front of the O2, and that will allow us to balance the oxygen. Now, the question that I commonly ask is this. When looking at a chemical equation, do you know what you should balance first? And the answer is sometimes. Sometimes you can tell what you should balance first. Sometimes not. Sometimes it's difficult to know. So sometimes it's a little bit of trial and error back and forth until we end up with equal numbers of atoms of all elements on both sides of the equation. So sometimes you can tell what to balance first, sometimes you cannot. You'll see what I mean. All right, here are kind of the steps or some tips for balancing chemical equations. First of all, always, always, always adjust the coefficients. We balance equations by adjusting coefficients. Never, ever, ever change the subscripts. So once you have the correct formula for each substance, leave those subscripts alone. Next, coefficients are ordinarily the smallest whole number ratios to each other. I will encourage you sometimes to temporarily balance using a fraction. So temporarily, we got to get rid of it, but sometimes that helps as well. Next, balance atoms that occur once on each side of an equation first. So if you have, like on our last example in the book, you had 2 oxygens on the right side, may want to balance that last. So balance atoms that occur once on each side first. And then again, with the oxygen, like here, number 4, balance elements that are by themselves last. So balance elements in compounds first. Balance elements that are by themselves, like O2, last. Go ahead and add this one to your notes. It's not in there. If at all possible, balance polyatomic ions as a single unit. Now, the only way you can do this is if you have the same polyatomic ion in the reactants as in the products. So if you have nitrate in the reactants and you have nitrate in the products, don't take it apart and balance the nitrogen separate from the oxygen. You're going to end up with a mess. Just balance NO3 as a single unit. So let's take a look at some examples. So I'm going to give you an unbalanced equation. And just for fun, I'm going to put some states of matter in there as well, just to kind of show you, just looking ahead when you write your own chemical equations. So sodium is a solid. Chlorine is a gas. And sodium chloride is a solid. I'll talk about how you know these states of matter later. All right, so let's balance this equation. Again, is it obvious what you should balance first in an equation? Sometimes it is, sometimes it is not. So pick something that is not in the same quantity on both sides of the equation. So first of all, let me read this equation to you. Sodium metal reacts with chlorine gas to produce sodium chloride. Let's balance this equation. So notice that we have an uneven number of chlorines in our equation. We have 2 chlorines on the left and we need 2 chlorines on the right. So let's do this. Please never, ever, ever, ever do that. This is what I was talking about before. Just because it makes it easier for you doesn't mean it is the right way. So we don't want to change the formula. The formula for sodium chloride is not NaCl2, it's just NaCl. So how do we make it so that there are 2 chlorines on the right side? Let's do this. Put a 2 in front of the Cl. No, we can't do that. Can't just put a coefficient in the middle of a formula. Try again. How are we going to do this? Yes, some of you are saying put a 2 in front of the NaCl. Now notice something here. If you put a coefficient in front of the formula of a compound, it changes the number of each atom in that compound. So though we've fixed chlorine, we've messed up sodium. And so now we just got to go fix sodium. So right now we have 2 sodiums on the right and we need 2 sodiums on the left. So let's fix that. And when you think you're done, double check. Make sure you have the same number of atoms of each element on both sides of the equation. We have 2 sodiums on the left, 2 sodiums on the right. 2 chlorines on the left, 2 chlorines on the right. This equation is balanced. So here's our next equation. Let me read it to you. Aqueous aluminum chloride, so a solution of aluminum chloride reacts with a solution of sodium hydroxide to produce sodium chloride, aqueous sodium chloride, and aluminum hydroxide, which is a precipitate. It is a solid. All right, so question is, what do you want to balance first? Question, again, does it matter what you, or is it obvious what you should balance first? Just by looking at an equation, can you tell what you should balance first? The answer is sometimes. Next question is, does it matter what you choose to balance first? The answer is sometimes it does matter. So what do you want to balance first? So we have a couple things that are not balanced. We have chlorine and then hydroxide. Notice we have hydroxide, the polyatomic ion, in the reactants in the product. So I'm going to balance OH as a single unit. So let's balance chlorine first. We have 3 chlorines on the left. We have 1 on the right. So let's go ahead and fix that. So once again, though that fixes chlorine, that messes up sodium. So now we have 3 sodiums on the right. We got to go over to the left and fix that. That fixes sodium and fixes hydroxide at the same time. So notice on the left side, we now have 3 hydroxides, and we already had 3 hydroxides on the right. So coefficients of this equation, 1, 3, 3, 1. Let's take a look at another example. All right, let me read this one to you. Aluminum metal reacts with a solution of copper 2 chloride to produce aluminum chloride and copper metal. So this time I think I'm going to let you balance it by yourself, and then we'll check our answers with each other. Go ahead and pause the video and do this one by yourself. All right, let me walk you through it and see if you use the same process. First thing I'd want to balance is chlorine. We have 2 chlorines on the left, 3 chlorines on the right. I'm thinking least common multiple. So what is the least common multiple of 2 and 3? That would be 6. So we want to make 6 chlorines on each side. So let's do that. So 3 in front of the CuCl2. A 2 in front of the AlCl3. And now we have some elements by themselves, which we can balance last because they're really easy to fix. So we have 2 aluminums on the right. So put a coefficient 2 in front of Al. We have 3 Cus on the left. Put a 3 in front of Cu on the right. Again, double check, make sure everything's good. We should be good. Let's try another. All right, so this time we have potassium metal that reacts with water to produce potassium hydroxide and hydrogen gas. This is a very explosive reaction. We're producing an explosive gas, hydrogen gas in this case. So this one, there's a little bit of a trick too, and it only works in this situation. If you have water on one side of the equation and a metal hydroxide on the other. What I'm going to do is I'm going to temporarily write the formula of water as HOH, and I'm going to balance the hydrogen separate from the hydroxide. So just to show a little division there. Now you can't leave the formula of water as HOH, but it's going to help us to balance this equation. All right, question, what do you want to balance first? Let's balance hydrogen. All right, how many hydrogens on the left? Go ahead and read that number to yourself. If you said 2, that is incorrect. Remember, we're going to balance the hydrogen separate from the hydroxide, so leave that H and OH alone. So we have 1 hydrogen on the left. Same question, how many hydrogens on the right? Go ahead and tell yourself. If you said 3, that is incorrect. Again, leave that hydrogen and hydroxide alone. We have 2 hydrogens on the right, so we're going to balance hydrogen by putting a 2 in front of HOH. So that fixes hydrogen, but it messes up hydroxide. So now we have 2 hydroxides on the left. Let's make it so there's 2 hydroxides on the right. We fix hydroxide, mess up potassium, go back and fix potassium. And then make sure to bring that coefficient down for water and cross off the HOH. If you don't believe me, check. I think everything should be balanced. Let's try another one. All right, here's our next one. Let me read it to you. A solution of sodium sulfate reacts with a solution of calcium phosphate to produce a solution of sodium phosphate and a precipitate of calcium sulfate. Go ahead and pause the video and balance this equation. What did you balance first? Did you balance sodium first, or sulfate first, or phosphate first? Sometimes if you choose to balance the wrong thing first, it causes you to have to change some stuff later on. So that may have been the case for you here. I chose to balance sodium first, least common multiple of 6. And then I balance sulfates, putting a 3 in front of CaSO4. And then we are good to go. All right, let's try another one. All right, we have ethane gas, C2H6, ethane, reacts with oxygen. This is a combustion reaction, this is called. And this reaction produces carbon dioxide gas and water vapor. The water here is a gas because this reaction is exothermic, so we produce water vapor. All right, let me walk you through this one. It's a little bit tricky. For these combustion reactions, these are probably one of the hardest to balance. So here's what we're going to do. Let me ask you this. What should you balance last? Really doesn't matter what you balance first and what you balance second, but it does matter what you balance last. Look at that equation. So with this, any combustion reaction, we're going to balance the oxygen, the O2, balance that last. So I'm going to do carbon first, and then hydrogen, and then we'll balance oxygen. So let's start with carbon. We have 2 carbons on the left. So let's make it so that there are 2 carbons on the right. We have 6 hydrogens on the left, so let's make 6 hydrogens on the right. And then we'll balance oxygen. Go ahead and count the number of oxygens on the right side. Pause the video. So how many oxygens on the right? So we have 2 carbon dioxides, that's 4 oxygens right there. 3 waters, that's 3 more. So we have 7 oxygens on the right. So we want 7 oxygens on the left. So here's a situation where I would encourage you to use a fraction. So notice it's O2, that's the problem. If it was just O, we'd put a 7 in front of it. But it's O2. So what times 2 equals 7? Let me write an algebraic equation. Because it's O2, 2 times some number must equal the same number of oxygens that are on the right side. So let's start off with a simple fraction. We get 7 over 2. Now, what did I say before? Can we leave a fraction coefficient? Nope, we need whole number coefficients. So we can temporarily have this fraction, but we need to get rid of it. So let's go ahead and take everything in this equation and multiply by 2. So we get 2, 7, 4, 6 for our coefficients. Let's try one more. I'll give you a tough one to try on your own. All right, here's the equation. Liquid methanol, CH3OH, reacts with water to produce carbon dioxide and water. If you're thinking of using that special trick I mentioned before about water and hydroxide, don't use it here. It's got to be a metal hydroxide. Methanol is not an ionic compound. So we're going to balance the oxygens separate from the hydrogens. I recommend writing an algebraic equation similar to the one I wrote for number 6 to help you balance O2. All right, give it a shot. See what you end up with. Pause the video. All right, so first thing I did is balance hydrogen. There's 4 hydrogens on the left. Don't forget about that 4th one there. So I put a 2 in front of H2O. That gave us 4 oxygens on the right. And so that's where I got the equation from. So 2 times something plus the 1 that's in methanol is equal to the 4 that we have on the right side. Solve for x, we get 3 over 2. Can't leave a fraction, so we're going to get rid of that. Multiply everything in the equation by 2. And everything should be good to go. That's how we balance chemical equations. I'll give you some to practice on your own tonight. Let me know if you have any questions. Thanks for watching.